Okay, so as we said, it's intensity we're looking at, and it's the power per unit area. And this formula up here is the exact same thing because area is under the line, and 1 over area is the same thing. That's area under the line multiplied by delta E over delta T. And that simply is the rate of change of energy per unit time. And that is also the definition for power. So this is all good. These two formulas are exactly the same. I didn't say it on the last slide, but the unit for intensity is watts per meter squared, which is consistent with the definition we had before, which was power over area. So, power is measured in watts and area is measured in meters squared. So this is all good. The faintest sounds the human ear can detect at 100 hertz. So it's all got to do with frequency as well. Have an intensity of about 1 by 10 to the minus 12 watts per meter squared. And this is called the threshold of human hearing. And this is a small number, as you can see, in terms of power, that is. But the eardrum is extremely sensitive. Okay, so it responds to this particular value of power, okay, at the lower end of its threshold. The loudest sounds the human ear can tolerate have an intensity of about 1 watt per meter squared. So this is really convenient, because obviously 1 is a very straightforward number to remember. 1 is 1. It's just a really important number. And then you've got, at the lower end, you've got 1 by 10 to the minus 12. So you can think about 12 hours, on a clock, something like that. Okay, so these are the two limits, the lower and the upper limits. Now, a more interesting thing is this thing called the relative intensity of sound, and this has got to do with a sound that's being emitted, whilst there are other ambient sounds, or sounds that are just in the surrounding area. Okay, and it's always good to use an analogy to explain this, and the one that I've used before then has to do with the pain threshold for humans. Okay, so my own common experience is if I ever stub my toe, that is extremely sore. And the first thing I do just to get over it is actually stick my other heel onto the foot, or even the toe that's been stubbed. And by using the secondary source of pain, it just dulls the other one. The other one is less intense. And this has got to do with, you've got two sources of pain now. So the first one doesn't seem as bad now. Okay, so we're talking about relative pain then in the case of that. With no other source of pain, the stubbed toe is extremely sore. But if you introduce another source of pain, i.e. the heel into the foot, it doesn't seem as bad, and that's an actual fact. It's the response of the human body. Well, the response of the human ear to hearing is also the same, and your ability to hear another sound within a kind of sea of sound is by comparing the two intensities. Okay, and this has got to do with relative intensity, so it's really interesting. It's called the bell, so you have a B here, that's the unit of it. The bell is equal to 10 log the intensity of the sound that's been emitted relative to this intensity here, which is actually the threshold of human hearing. That's what's used as the baseline intensity, I0, and then you have your emitted sound and you compare the two of them. But this figure is 1 by 10 to the minus 12, the I0 subscript 0. Because bell is quite a large unit, often in cases the decibel is what's used, and that's what most people are more familiar with. So now you've got your decibel scale here, and you've got a decibel of between 40 and 50 would be hospital environment, and at the upper end of it then in red you've got 110 decibels, which is a rock concert. Okay, conversion examples then. The first one, we're using an intensity I of 1 by 10 to the minus 12, which is the threshold, lower threshold of human hearing. And then to find the relative intensity, we're using 10 log, and you put the intensity over the intensity, the baseline intensity, which is I0, and the two are the same, so there's no relative difference between them, and therefore that's 0 decibels as expected. Okay, the next conversion example then, we're looking at a 1 by 10 to the minus 11 relative to the baseline again, and this time we end up getting 10 log 10. And you just type in, plug and chug in your calculator, log for log, not ln, natural log. Okay, so it's 10 multiplied by log 10. And when you do that, log 10 gives a value of 1. Okay, so and 10 by 1 is 10 decibels, and that's your answer for that. Okay, and the last concept from this area that we need to look at then is the idea of spherical and plane waves. Well, spherical waves can be imagined by, if you have a sound, a point source of sound. Well, the sound is emitted in all planes, i.e. Up, down, left, right, basically in all the planes that you can imagine. And so what that means then is that you have a sphere of sound that's progressing. So it's a spherical progressive wave of sound. That's what you've got. Okay, and as the sound moves from the source, moves away from the source, the intensity decreases, and the experience of that is obvious. An explosion being right beside it versus being a distance away. It's not as intense. So to work out our intensity, we go back to the basic formula that we had, which is power over area. Intensity is equal to power over area. We're introducing the idea of average power then in this case. But nonetheless, it's the same idea. The thing that differs this time is the area, and the area is what's called the surface area of the sphere. Okay, so this formula, you can find it on the internet, or if you have a set of tables that have formulas in it. The surface area of a sphere is 4 pi r squared. So we use it consistently then with the spherical progressive sound pattern, and work it from there. Okay, so remember, you've got this sound wave which is traveling past every point and passing through every point, which means that as the sound wave, the wave front, approaches a particular point, it has low power. As it meets the actual point, it reaches a maximum power, and then as it passes the point, the power dissipates again until the next wave front comes along, and then it reaches a peak and it drops off, etc., etc. So the entire time you've got power from the sound wave at the wave front, and the wave front is maximum power, and either side of it then would be less than that, but you average the power from that then. Here then we're comparing the ratio of two intensities as the spherical sound progresses. So we're talking about I1 over I2, two different intensities at two different distances from the point source. And it conveniently then simplifies down to R2 squared divided by R1 squared. And where that's coming from is the very definition of intensity at two locations. Intensity at location 1 is the average power divided by 4 pi at that radius R1 to be squared. I2 is the very same, except we're talking at a different radius, so it's R2 squared. What happens is that when you divide the two of them, put one over the other, p average cancels above and below. So too does 4 pi. It's common both above and below. Now R1 squared and R2 squared are not the same, so you can't. You're not in a position to cancel them off. And because R2 squared is under the line under P average, and it's also under the line given that it's I1 over I2, it actually inverts and ends up on the top line. So you get, it's a double inversion if you like, so you end up with R2 squared over R1 squared, and this is just a formula then that you have for the intensities, the ratio of two intensities. It reverts down to a simple R2 squared over R1 squared.